Could you hear me?
Yes, sir, you're audible.
My screen is visible and I am audible, correct?
Yes.
Perfect. So let's do some recap. So we were trying to see controllers. So, so eventually controllers means what? So it is a device or a soft device. So device means of course software or a hard device, which means that it is a hardware element, which takes, so let's say this is your controller. It takes error signal because E is C. E physically it is E, but for system it is an error signal because it is computed. This is corresponding to an error which is so again let me draw the entire control loop once. So you have the process which I will call it as GP. Okay, before the process there is final control element which I'll call it as GV. Before the final control element there is I to P which I call it as GIP, and before that you have your controller which I'll call it as GC, and this process is continuously operating and its output is your Y or YM. Let us call it as Y or YM, and you would have a sensor which I call it as GS, and GS would measure. So it's like assume this is a wiring, and sensor would give you signal corresponding to actual YM. So see, this is YM, but this is not YM. The output of GS is not YM. You understand that? So this is a signal corresponding to YM, with whatever may be, because this is sensor. Okay, then sensor would go. So because this is overall system, and you have a comparator, it would be hardwired, and you would give set point. So mind that this set point is also converted into signal. Set point in signals. Why? What I mean by signal here is, let's say you're 350. Let's say you are trying to control temperature and 350 Kelvin is your set point, because that is what you need to achieve inside the system. See, from the GS onwards, it is all. So from here onwards, it is all signals, which means that whatever you are getting here is YM. Okay, I'll put GS. YM equivalent to a signal which is equivalent to YM, but it is converted into the sensory what you call domain. So from here it is all, maybe most of the sensors, as we all know, this would be all 4 to 20 milliamps or 1 to 5 volt. So this would be the outputs everywhere in this line. So when you put 350 to the comparator, it doesn't understand. So see, this would be minus and this should be plus. You have a set point and you would calculate the error, and this error would go inside the controller, and this process operates. My point is, let's say this is So the signal here is 15 milliampere. And comparator is nothing but it's a mathematical manipulator. It just subtracts or adds or whatsoever. So you can do by means of circuits. You can add or subtract two signals. So you give something equivalent to 350 here. It doesn't make any sense. So you have to convert. So you should know the conversion from. So let's say x is your original variable value. X would pass on to GS, which is your sensor. You would get X GS. So this is your original variable, original value, in fact, original value. So let's say it is 350 Kelvin, this is 350 Kelvin, but this is sensor equivalent of that. Sensor equivalent signal. So let's say if your temperature and let's say it is varying between 300 to 400 Kelvin, your X would vary between 300 to 400 Kelvin. But your XGS still would vary either between 4 to 20 milliampere or 1 to 5 ohm. So when you put the set point as 350 volt into the comparator, it doesn't make any sense for the overall process because 350 is not what you really need here. You should do the same conversion. So you know that what is the model of the GS and it takes GS and corresponding to make it to XGS. So you have to apply the same sort of a transformation and apply a set point as a signal value. So this would be again of the order of 4 to 20 milliamps or 1 to 5 volt. Okay, then of course, then both of them, then the error. So this error inside the control system is not really the true error. So your true value of y may be 320. Let's say call it as ym is 320. Okay, and y set point is 350. So the error in true variables is 350 minus 320, which is 30 Kelvin, whatever. While error inside the loop, this error signal inside the loop is okay, it would be like this. So let's say 18 milliampere is the sensor equivalent of 350, which essentially means that that is the value that you need to achieve, and 320 may be corresponding to 10 milliamps. It will not be that much, maybe 15. If you scale it uniformly, it may be 15. And this error, so this is physical variable, and this is in circuit. This would be like 3 milliamps is the error signal, which would be going to the controller. Okay, controller would do necessary transformation and so on and so forth. So what I'm trying to say is controller is essentially a device that takes an error signal and do certain transformation and gives you what is known as the controller output, which would be fed into uh, various downstream devices, be it I2P or control valve, so on and so forth. Okay, so now coming to this conversion. So what you really need to do is you need to take ET and make it as PT. Okay, and you have either it could be hardware or software or hello.
Yes, sir.
Hello.
Hello, sir. Are we not audible?
Could you hear me? Hello.
Yes,
Yes, sir.
sir.
But
No, I thought there was a audio cut in the middle, and I just kind of thought that uh, you could not hear you, so I just kind of logged out and logged in. So I hope now it should be okay. Yeah. So
Can
I can also see your chats here. You can hear me. Cool. So let me continue. So what you really need, so in terms of hardwiring, so it is a circuit, while in terms of softwaring, it is an algorithm. So algorithm would just give you some p bar value. So there is and I'll tell you there is one more difference. Okay, if it is circuit, p of t is coming out directly as signal. Because it's a circuit, right? It takes a signal, do some manipulation, and the resultant goes out as a signal. While algorithm, it is a number. So algorithm would give you an output. What is the value of p of t? So it essentially means that because that is not good enough, right? So algorithm is just a soft number. So physically, I think as I told last time also, you need to have a source attached to the algorithm. Source means electric source. So this P of T is a query. So you have a DC supply attached, and you would send in a instruction. Okay, a signal worth P of T you should release, and this comes out, and this would be the real P of T. So I will like to write that this P of T soft, and this is P of T signal, and this would again go back to the plan. While here it is directly, if it is a circuit, it is a direct transformation. Please visualize this, okay? How this is happening. I don't know how you could do, because I am really kind of surprised, or rather uh, to see that you could not able to visit a proper chemical plant to understand this. But I think it's okay. Please, whenever you get a chance, you try to correlate. So I'm trying to give you as much as possible from a physical perspective, so that I hope it will help you to visualize what is happening. So these details may not be there in the textbook, okay? Because textbook is all about computing a controller. So assuming that controller, so they have written the fact that all of these things is there, assuming that you know what it is. So that's why I'm just going a little bit more into the practical aspects of it, so that you would at least be able to visualize this to some extent. Okay, so now we have looked at three types of controllers. So see, just P, okay, let me come to that. P, PIN, PID. So these what you call, these type of controllers are basically called as uh, these are the controllers that would directly interact with the plant. So see, you take the error and gives you the output. There is one layer above this. So how do you get the set point now? So set point, you can either this from my experience, so which means that you have some idea how things are operating, and you give the set point, because set point is something that you need to provide here, you see. So this may be either known from experience, because you have various people working in the plant, and they would put these numbers in here, and they know these are the numbers that you need to get your product quality at the desired level. So in the real plant, this is coming from, so let me also put this. So this is P, PI, PID. Okay. Whatever. So even though I write it as P, PI, PID, as I told in the last class, this is just a one device which contains a P node, I node, and D node. I hope you will get a chance to see this in the process control lab. Okay, and there would be a knob that you need to operate, and there would be a number written on the top. So if you want only I shut off both P and D. If you want only P, shut off I and D. If you want all the three, activate all of them. So as I told, the set point is the key thing that you need to provide here, because this is external to the system, because whatever going inside as signal, in fact, see, most of the system, so let me just not confuse you, give me a minute. The one layer, just one more level above is where you send in this. So this here you would supply this would be the measured value of the sensor, and here is your set point. Plus and minus, most likely set point value you take it as the standard, and of course otherwise it's just a sign change, and you can accommodate things. So where is the source of set point? So set point is either, as I told, either you know it from physics, or somebody who is already has well versed about it, and they will put a fixed number. So in real plant, what they do is they do know something known as set point optimization. So what do you mean by set point optimization? So set point is just not given as this number. So you have some level of calculation went inside, most likely done to see you. So the number that you put in, let's say 350 Kelvin whatsoever, for instance, would have a strong bearing on the overall control system performance, overall production. So it's very important that you know this number as accurate as possible. So in real industry, they would obtain this by solving some optimization problem. Yeah? So this could be a I'm sorry about it. So this could be either. So what do you mean by set point optimization? So set point optimization, you should see this number what you put in over here would have bearing on your next 1 week's performance, because you might keep the same number, or maybe let's forget about 1 week. Nobody is going to change this number every now and then. If you are changing every now and then, essentially means that you don't know the value of the set point. So you would like to keep it as constant as possible and tweak it based on your need. So basically speaking, you would, so set point, once you fix it, you don't typically not change for some time. I'm sorry about it. So coming back to this, so you don't want to change this every now and then. So you basically, this optimization is done by doing a forecast over 1 week or so. So you know what you need to produce for some point of time. So let's say you assume 1 week as a for what you call a safe period. So you are forecasting what you need, and you need to produce so much of things, and you need to have. So for instance, right? So every day that you produce, so eventually look at this process. So you are selling things to the market. Okay. So so basically all production is highly market driven. So let's say for 1 week you are deciding you would produce. So for instance, consider, let's say you are producing, let's say you are doing let's say you are doing the production of a particular pharma product. Okay, so what would happen in this pharma product? And you would calculate 1 week demand. You know what the sellers, your buyers, or your market has given you as schedule. So you may need to produce one metric ton of certain product. So you forecast this. So you would forecast what is that, what is the real amount of production details that you need, and you minimize this with respect to your operational variables, and these would be given you as a set point. So once the set point is fixed, okay, then your PPAD controllers are going to operate by directly interacting with the plant. While the set point optimization, right, you are not feeding the set point optimization or set point whatever you are getting directly to the plant, because these are the real guards in the field. You are only allowed to change the set points because they know how to interact with the plant, because PPAD controllers are uh, clean enough to deal with the plant details. So now coming back to the overall. So see, what you understand in the large scheme of things, this PID controllers are not the only one that is doing the show. You have an optimizer module which is just lying on the top of this PPA and PID controllers. These layers are either called, okay, real-time optimization. Sometimes, so I don't know somebody who would I don't know whether someone of you would take this course on advanced process control next year or in your next semester. Then you would hear something known as model predictive control. This is also or dynamic optimization. So these two are the two layers, two things that would come in the set point optimization scheme. And the set point optimization gives set points, then PPAD and PID controllers are ready to do things in the field. Now, where we have stopped is seeing P, PI, and PID, because they are really interacting with the plant. So now let's look at a bit more onto how it is being implemented in detail. So this whatever you see over here is a circuit implementation of PID. So this is particularly known as the series form of PID controller. This is particularly known as the parallel form of sorry. So this is the parallel form, and this is the series form. So by name, because things are parallel here, things are series here. Because circuit also parallel circuit, series circuit. See again, this is the hardware implementation. You please understand this, okay? So now look at, see, so we know three things are there in your PID. One is of course the P, one is the integral term, and the derivative term. What the parallel implementation of the PID does, okay, in the hardware, take the error signal, okay, it just apply this to the I element, P element, and D element. So what it does is, okay, so let's do this like this, okay. your P of t is P bar plus K into Et, 1 by tau I times, okay, integral of Et dt plus tau d times, just a second, I don't know what 1 by tau I times integral of Et dt plus tau d times det by dt. So this part of course has been proportional, this is integral and this is derivative. So if you see over here, so leave out this, oh, some issue, so just give me a minute, apologies. Okay, I hope my screen is now visible. So the way it is generally technically implemented would be either to take the error, feed into the P block, take the error, feed into the I block, take the error, feed into the derivative block, okay, combine everything, plus, and add into a, so let's check this, what does this mean? So this is P of t. So most often times you keep so see this proportional gain to be unity. Integral gain would be 1 by Et by tau s. So this would be tau d times s. So your signal is splitted and combined everything and just multiplied by a constant. So why are we doing this? If you look at this whole expression, right? So Pt is equal to P bar plus K Et plus 1 by tau I integral Et dt plus tau d times Et det by dt. So you can always take a common factor which I will call it as Kc. Okay, and this Kc, however way you want to do, okay, and you can just take care the remaining part of it. Okay, so this could be, so I will write Kp times Et, and tau I will write tau I prime because I have taken a common factor out, the new tau I, and tau d, I'll put a new tau d because I have taken something common. Det by, yes. So what would happen? So these tau I, new tau I is basically the factor that is taken out of outside the whole bracket. So just to make things more simple. So here what are we trying to say? To have a scaling factor which can kind of scale up the entire what you call circuit's output. So this is sort of an amplifying term. So let's say the overall output is not still you feel like it's not really doing good. You have another handle to scale it up. So that's what this KC does. Okay. So now if you look at the overall implementation, you would have these three terms. So most often times your KP would generally so when you take the K out, right? So Kc out, then the remaining term is Kp. You generally assume that to be one unity because you don't want too much of proportional kick. If you really want a number, you are free to put Kc over here also. So that the takeaway message here is that the signal would be sent into three different electrical blocks and finally summed up and scaled. Okay, so that's what it does over here. So so this is the overall base circuit implementation of what we call parallel form. And there is a series form also. So see, if you look at the PID controller equation, you have P, I, and D. So physical realization of this in terms of a parallel circuit is much more easier because three terms, right? So you only need to split the signal and feed into the P part, D part, I part, and D part, and each of these would do their own manipulation, and final output would come. But there are certain what you call issues over. So this would again result in splitting, combining, so on and so forth. So basically, there is also possible. So these are electrical wires or electrical connections, right? You are unnecessarily adding more connections also over here from a practitioner's point of view. Then somebody proposed that you can do this, you can get away this parallel form, and you can also write an equivalent form as a series form of PID controller. What they say is, in that case is you have a PI and PD terms, you can connect them in series. So basically what you are trying to say is, instead of splitting them together, you make a PI circuit and a PD circuit separately. Okay, and if you need to, if you this amplifying factor, you can either keep front or in the back, forget about that. Okay, and error signal, you pass them one after the other. So first back to the PI thing and back to the PD thing. What would happen? Your P would be doubly acted. So it is PI and PD, right? So the P proportional fraction would be doubly acted on the system. So this is the overall series form of the PID controller. But again, so here the good thing is that you have lesser number of tappings. So here you have multiple splitters and multiple combiners, while in the other form, okay, you have limited number of taps, but your P value would be doubly acted because it's a combination of PI and PD. So if you factor in, P is the effect of the P is counted 2 times. So again, so these are hardware implementation. So there is nothing you could do because you have with a resistance, okay, with the capacitance and with the source and wire, this much you could do in reality. But despite of the fact that there are multiple tappings and multiple joinings, this form is very close to the theoretical PID controller structure. Okay, so this is what would be most widely used everywhere. So the parallel form of PID. And you can also split them and write now. So this, you have a Kc term, and this Kc by tau I you can write as a Ki term, and this Kc times tau d you can write as a Kd term. So why I am saying, because you might see various, so when you go to the control lab, you might start seeing various way of writing things. So sometimes it would ask for a bias, then it would just ask for something known as the proportion, the contribution from the proportional term. So you have to just put the Kc directly. Then it might ask the contribution from the integral term directly. So they might not ask your tau I, but they would ask for Kc by tau I. So this is generally known as Ki. And again, so when you go to the when you see physical controller, if it asks for tau d grade, because see, these are different manufacturers, right? So they would So when you are working with hardware, people think there are various. So it's like buying an object from different vendors. So some would like to put these numbers are KC, tau I, tau D, but someone would like to do it as simplification input. So for instance, Ki, there is also Kd times dEt by dt. So while Kd is Kc times tau D. So this you might see this version also available in the market. If you come to the lab, you might most likely see that you will put the integral term. So they will just ask what is the derivative term, which is Kd, integral term, which is Ki, and the proportional gain, which is Kc. So this is also one what you call one way of representing the whole thing. So the standardized representation include Kc, tau I, and tau D. Hello. Hi guys. Could you hear me?
Yes, sir.
So my screen is moving? Not right. Because I see some level of internet disruption here. Give me a minute. So let me rejoin. Some issue. I am unable to share my screen. Give me a minute. Huh? I'm sorry about this. Yes, at least I could join back. Let me see what I can, if I can share it. I think now it should be possible. Just me check. This device. You can hear me, right?
Yes, sir.
Okay, so now okay, so now the other issues. Give me a minute. The multiple power cuts in the department. So then it just, even though power comes immediately back, right? So that one moment your internet get disrupted, then things go away. Okay, so now we were trying to see which are the two hardware implementations of PID controllers. One is of course parallel and one is series. Now, so we have seen, so do two good things about PID. So one, so first of all, the P part would give some initial pull, okay. Then so see, so look at these two terms. So the E and okay, so it's not here, so I'll have to go over here maybe. So okay, look at these two terms. So let's say there is a sudden spike in set point. Okay, so what would happen? So E would be Y set point minus Y actual, right? So what would happen is your error would shoot up momentarily. So it would be a huge shoot up. So what happened? This particular term and this particular term, which is dE by dt, because there is a change in output, so dE would also be very high. So these two terms would be spiking up. So this is generally known as, so of course et by dt would not have any problem because it would keep on integrating and integrating, and after only it would effect would be too much, and also you are dividing it by tau I. So the general effect on the integral term would be not that significant, while kc and tau d, so this the proportional part and integral part would have a big kick. So it is technically known as proportional kick and derivative kick. So kick in the sense that d by dt would become sufficiently large, et becomes sufficiently large, and a huge momentum to the, so there is no problem as such, but only issue that you would suffer is your control valve, which is your final control element, would see a sudden spike in terms of your stem movement, moving back, movement and back. So this might eventually hurt your diaphragm and the plug, and this would very quickly get eroded. So to avoid this proportional and derivative kick, there have been minor modifications in terms of uh, in terms of PID controllers. One thing that they do is you might eliminate this scaling parameter. So no scaling. So as a result, what it would not plug too much. The output will not be will not be varying too much, and also you see your instead of your error term, you would change your term to dy by dt. So what is dy? So this ym is the actual output. So actual output, previously it was error, which is the difference between set point and ym. Since there is a sudden change in the set point, error would be very, very high. So your dE by dt would be very high, and overall the controller would do a derivative kick. To avoid that, you just cut out. So just to avoid this kind of scenarios, instead of YSP by YM, which is E, you just use YM over here. So what is the difference between both? Take a look at here, okay? And you are operating, and so I'm just, so this is your Y and this was your set point. And you did a set point change, correct? At this point. And this is time and ym, let's say ym was very, maybe blue, ym was very close to the set point, then your set point did a jump, so this is your set point. So what happened to the error? So if you plot the error over here, error would also do a big jump. So as a result, this much effect would go to dE by dt k times dE by dt. This will be very large. But if it is ym, if you use actual process variable, what would happen is this was the expected set point. It would again just take a slow change. So the controller will take time to stabilize ym, right? So as a result, it will take some time. This is the profile of ym. So you see that the ym will definitely have a smoother response compared to YSP minus YM, because YM is the actual process variable and it would tend to tend to kind of change in a reasonably slow fashion only. So just to avoid this E being a derivative kick, as a workaround solution, people have also suggested disregard YSP from the E calculation. Just use the ym, which essentially means that your response, ym response would be smooth. Eventually, it would do catch up, okay, set point. So this sharp jump would be avoided, but it would take a smooth excursion. Okay, so just give me a minute. Sometimes everything. So this is what I have told. You would, instead of your ET, you will only use IM. So another point that one more option, okay, to deal with such thing is what is known as weighting. So what in this context they would do is instead of the true error E and true error E were, so this is the proportional term, and this is the derivative term. Integral term, of course, there is no problem because it is a smooth integration. Okay, so if there is a sudden change also, it would just manually accumulate the error. So to 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 kind of consider, to kind of accommodate the sudden jump that is taken by the E signal, because this would be sudden jump. So instead of using E directly, people tend to use, okay, weighted set point, which in this case you call it as EP and ED. So how do you do this? So the E generally is obtained by multiplying some constant beta with respect to the set point. ET would stand as it is, while ED is obtained by multiplying some constant gamma to the set point. So there are multiple options now. So what I am now trying to say is my controller dynamics is P bar. This is P, P of T is now E. What was the term? EP. Okay. EP. Okay. Time EP times T. Okay. So integral term stay as it is. Derivative term is tau D times T E D by dt. While EP here is beta times YSP minus YM, while ED is gamma times YSP minus ym. So there are multiple options now. You can have a, so if you put 1, you will get your original formulation back. If you could put 0, it would be like you would completely eliminate derivative k. But you can also do what you call a smooth change of profile. For instance, instead of keeping this beta as a constant, you would vary between 0 to 1 over a time. So as a result, your YSP, right? Original YSP, it was a jump. This was original YSP. And if you weight beta between, let's say, series of values between 0 to 1, you would also get a smooth weighted set point track. Let me do it in a very different color. So, like this. So this is weighted set point. Fine. And if you don't weight, so it would be like fully eliminated. So you put not weight. You do full weighting. So you put like beta to be 0. This would be much more slower. So here it is beta is equal to 0. Huh? So this is a smooth weighting of beta over a period of time. Okay. And this is no weighting. So you can play with this beta. This is of course for integral. You can also do the same for the derivative case by tuning your gamma. So what is the advantage? You don't bump your controller output because it would be smooth bumpless or smoother transfer. Because otherwise you would see that your controller output is dramatically changing, and as a result, uh, the final control element and even the process would be simply what you call put to a shock. It would just do a bump in the overall system. So now few more points. There is also a notion of direct and reverse acting controller. So if this Kc term is positive, you would call it as a reverse acting controller because it would, and if the Kc is negative, it will call us direct acting controller. We can also see.
Robin has grabbed the opportunity.
Hello. So there is some conversation. Anything that? Hello. Amit. Hi, Amit. Hello.
Got it, sir. He muted. He muted.
Okay. So there is also an on-off control strategy. On-off control instead of a PID control, what it would do is it is generally for non-critical industrial application. Basically, you would see is the simplest on-off control that you would see in your home would be heater. It would cut off, or even AC, which are non-inverter AC. When the temperature goes
Hello,
above,
sir.
yeah.
Sir, just
Go
a
ahead.
doubt. Can I ask right now?
Please go ahead.
Sir, so if we are using that weighted method for our SP, then we
Ah,
don't need to discard the SP, right?
correct, correct.
Okay.
So, so you can fine tune your beta, what in whatever way we want. So discarding would be a slightly, so see the difference you would see. Now when you discard, the overall process become very slow. See, it takes a longer time. And if you don't put beta, it would be a full bump. But if you put a smooth beta, you would say individual. This is basically the weighted set point, so that you won't bump your controller output directly. Is that okay?
Yes, sir. Sir, and also, sir, why we are preferring that parallel form over series? I did not understand that part.
Okay, so let me go there. Okay, so parallel form So when you have series form, you would double count your P. This PI and PID, you see that?
Yes, sir.
While in parallel, that won't happen, but you would have only additional challenges related to multiple taps and multiple connections. And parallel form is very, very close to what we have learned as PID because it has, while in the other case, it is like combination of PI and PD, which eventually it will become PID because, you know, by the principle of transfer function, it all get multiplied, right? PI will become multiplied by PD would become eventually a PID, but you would do a double counting of P. Is that clarified, Shruti?
Yes, sir.
Any more questions? Okay, so then I will just stop in the couple of minutes generally how the responses looks like. If there is no control, let's say this is your set point. 0 means that the error is 0. No? So don't assume that y, let error is 0. This is the point that we need to track. If there is no control, it would go wherever it wants. If you use only proportional, as we seen that there may be a bias, and only become k tends to infinity, this what you call the bias or offset will be removed. If it is just pi, you would see more oscillation, but there would be lesser, no offset. But if it is PID, you see that it would be much more milder, and eventually it would become more manageable. So always better to have PID, then PI, then P. That is your order of preference. So now we can also check how it looks. So if you increase the Kc value for PI control, if there is no control, it would be a bias, and if you increase, you would see that it would, this offset would keep on coming down. Fine. Then if you increase tau I for a PI controller, what would happen is the performance become more smoother. The decrease in tau I would go more oscillation, and P's effect would be as it is. And the same applies for tau d. If you increase tau d, the level of oscillation would keep on decreasing because this is accounting on the rate of change of error. And I will stop here. Now, this we can consider in the next class. This is a digital version of the PID controller.
Right.
Okay, guys, then.
So,
Okay.
sir, a tiny question on the follow-up for the quizzes. Would the pattern be like, how would the pattern be for the 12th October quiz, and what would be the syllabus for it?
Okay, the syllabus would be as of today because Friday there is no class, no?
Okay.
Correct, right?
They would be
Do we have
this. They would be.
No, sir. I guess
we have
Friday is midterm presentation of project, so the classes
Oh,
are.
right. Got it. Got it.
so do we have a follow-up class on Saturday?
No, sir. I don't
No,
think.
sir. No, sir.
Okay, so then we will only see this questions in the tutorial, right? On Monday. So the content would be whatever I have taught today, whose tutorial would be taking on Monday, and the previous chapter, which we have not covered in the what you call in the quiz.
Sir,
So
in the
you
minor,
could
right?
you could yeah, you sorry, in the minor. So you could count the last two tutorial contents. So
Fine, sir.
sorry, the previous tutorial and the coming tutorial. That would be the overall contents. Got it? Ashutosh and
Fine, sir.
others?
Yes, sir.
Perfect. In
Right,
terms
sir.
of the pattern, I think we would still keep it in the what you call in the online what you call this thing, but we'll try to do some variation in the overall questions. That's all.
Okay. Got it.
Okay, okay, guys. Bye bye.
Thank you, sir.
Thank you, sir.